Okay, good morning, everybody. So we were discussing Bernoulli processes last time. So it is simply a sequence of IID Bernoulli random variables. I guess last time I denoted them as xn's, or let's say xi's. Right? IID Bernoulli random variables with a common parameter p, probability p. And based on this, we looked at the more interesting process, which counts the number of successes up to time n. So this Sn has the binomial distribution with parameters n and p. And the process Sn is Levy, meaning that it has stationary and independent increments. We checked this last time. And we also looked at the times of successes. So this is the first time that our success process hits the level k. We also looked at the distribution of tk. Right? We looked at the event that tk equals n, and this simply means that this simply means that we have up to time n minus 1, k minus 1 successes, and the last one, xn, is also a success. And before doing the probabilities, so we can also see that this is, so since this is x1 to xn minus 1, so this is measurable with respect to the sigma algebra generated by x1 to xn, by this vector, let's say x1 to xn, right? So if you call this Fn, what you get is a sequence of, increasing sequence of sigma algebras. And this is called the filtration generated by the process X. Okay, so the family Fn of sigma algebras is called the filtration generated by the process X. You can also check that this is the same as, so the sigma algebra generated by x1 to xn is the same as the sigma algebra generated by s1 to sn, simply because x1 to xn and s1 to sn determine each other. If I tell you the values of x1 to xn, you can calculate s1 to sn, right? Just sum of xi's. And if I give you s1 to sn, then you can tell me x1 to xn, because x1 is s1, x2 is s2 minus s1, x3 is s3 minus s2, etc. So these two vectors determine each other, right? Therefore, they generate the same sigma algebra. Determine each other. So they generate the same information. Determine each other. And in general, any sequence, let's call it Gn, of sigma algebras is called a filtration if G1 is a subsigma algebra of G2, etc., etc. And this Fn that we define this way is called the sigma algebra, the filtration generated by the Bernoulli process, or the process of successes S. Okay. So we say that random variable t from omega to n and possibly plus infinity is a stopping time with respect to the filtration G if t less than n is Gn measurable for all n. Okay? And you can also check that this is equivalent to having t equals n in Gn. As an exercise, you can check that if you have t equals n, that is Gn measurable for all n, then t less than n, less equal n, is also Gn measurable for all n. So this is called a stopping time. So the idea of stopping time is as follows. So stopping time is a random time. So because its values are times, right? Okay, so it's the time of something that is random. And the condition, the measurability condition here is saying that we should be able to tell if this random time is realized by time n, if this random time is realized up to time n, we should be able to determine this based on the information that we have by time n, at time n, okay? So in other words, it's like an alarm, okay? So you don't know when it's gonna sound, when you're gonna hear that, but the random time that you're gonna hear that is determined by the information available in the environment, okay? So the time when it's gonna appear, when it's gonna show up, is determined by the information. It's just a random time, okay? Doesn't mean it's deterministic, it's just random, but it is determined by the information that is growing in the physical environment. Because this Gn is increasing by time n, okay? So the event that you're gonna hear it by time 3 is G3 measurable, whereas the event that you're gonna hear it by time 4 is G4 measurable. So it's measurable with respect to another sigma algebra. So it's not just measurability with respect to a single sigma algebra, but it's measurability with respect to a growing body of sigma algebras, namely a filtration, okay? So this TK, so back to TK, so the reason I'm talking about this stuff is as follows. This TK is a stopping time. Stopping time, because we wrote that this is Fn measurable, right? This is determined in terms of Sn minus 1 and Xn, and this is Fn measurable. So Tk is a stopping time with respect to the filtration Fn. So it's not just one of those fn's. It is the whole filtration, okay? So it's not a simple measurability criterion. It's more than that. And this k is just 1, 2, 3, 4. So for each k, this is measurable. This is a stopping time of the filtration. Okay. So I guess we looked at the distribution of tk, but let's do it again. So this probability that tk equals n is simply the probability that Sn minus 1 is equal to k minus 1. So using the binomial distribution, this is n minus 1 choose k minus 1, p to power k minus 1, q to power n minus k, times p, because it's the probability that xn is 1. Okay, so this is for n, k, k plus 1, etc. Okay. We call it negative binomial distribution. And if you look at T1, this is just q to n minus 1 times p to k minus 1 and p. You're going to get just p to k, which is just p. So this is for n from 1 to 3, simply n, right? So this is we say that T1 has the geometric distribution. And you can also calculate that the expected value of this is, so n times the probability that T1 equals n, so q to n minus 1 times p, n from 1 to infinity. So this is a geometric, this is the kind of the derivative of a geometric sum, right? You have n and q to n minus 1. So if you go through the derivation of this kind of an infinite series, you're going to get that this is equal to 1 over p. So if you evaluate this infinite sum using the old calculus trick, namely seeing it as d dq of q to n, and then swapping the order of derivative and the infinite sum as you did in calculus, so you can check that this is indeed 1 over p. So the expected value of geometric is 1 over p. Okay. So let's also look at the joint distribution of T1 and T2. T1 and T2 minus T1. So this is the inter-success time, right? Inter-success time. So what is the probability that T1 equals I and T2 minus T1 equals J? So since this is the time between the first and second successes, it can be 1, 2, 3, 4, right? And this can also be 1, 2, 3, 4. So what does that mean? T1 equals I and T2 minus T1 equals J. So this means we exactly observe the following situation. So we have failure, 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 failure in the first I minus 1 trials. And then we have a success at the ith trial. Then we're going to have failure, 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 failure in the next j minus 1 trials. And then we're going to have a success in the I plus jth trial. So this is exactly saying that x1 is 0, xi minus 1 is 0. And if I equals 1, you're going to have no such terms here. xi is 1. xi plus 1 is 0, xi plus j minus 1 is 0, and xi plus j is 1. So this is we have I minus 1 things here, and we have j minus 1 things here. Okay, so these are just IID, right? So this is q to I minus 1, p, q to j minus 1 times p. So if you look at that, this is just product of two, what kind of distributions? Yeah? Geometric distributions. So what I'd like to conclude is that T1 has the geometric distribution, T2 minus T1 has the geometric distribution, and they are independent. How can I say that? So I do this calculation, and I want to say we're done. We're done. I can just say that T1 has the geometric distribution, T2 minus T1 has the geometric distribution, and moreover, they're independent.
We know their marginal distribution, and when we just multiply them, we get the joint. So can we just conclude that they're independent?
First of all, how do we say that, for instance, T1 has the geometric distribution? In another calculation, we could have got two different distributions in multiplication. How do you assign one to T1 and the other one to T2 minus T1? Well, because this is T1 equals I, and I have I here. So this is the distribution with I, and this is the distribution with J, right? But of course, how do we really say this? So how can you get rid of J in this calculation? Just sum over all J's, right? Then this is going to disappear because this is a distribution, so its summation is just 1. So just take infinite sum over J. You're going to get T1 equals I is Q I minus 1 times P. Just take sum over I's. You get T2 minus T1 equals J equals Qj minus 1 times P. And now we know the marginal distributions, and we know that the joint distribution is the product of them. Moreover, we have T1 and T2 minus T1 are independent. Okay? So this is for all I. This is for all J. So this says T1 is geometric with P. This says T2 minus T1 is geometric with P, and they are independent. So I did this just for two inter-success times. So this can be generalized to the following fact. So T1, T2 minus T1, etc. Let me write one more. T3 minus T2 are IID geometric P random variables. Okay. So by the independence of infinitely many things, I really mean that every finite subcollection of them form an independent collection. Okay, that's the definition of an infinite independent collection. Okay, so for instance, I can write Tk as T1 plus T2 minus T1, etc. Tk minus 1. And then I can calculate the expected value of Tk using the fact that expectation is linear. So I just have k of 1 over p's. And remember that Tk is a positive random variable. So this k over p is just finite, assuming p is strictly positive, right? Let's assume p is strictly positive. So you have Tk that is a non-negative random variable, positive random variable, whose mean is finite. What can you say about this random variable? So you have a positive random variable with finite expectation. What can you say about that? Positive random variable with finite expectation. Can it be plus infinity? Can this random variable take plus infinity? With 0 probability, right? So we can say that Tk is finite almost surely for p positive, strictly positive. Tk is finite almost surely. So this is sometimes called Murphy's law. If something can go wrong, it will go wrong, right? So this is, if you think of T1, for instance, it is the time of first success. So if something has strictly positive probability of happening, it's going to happen with probability 1. So T1 is finite almost surely means what? You're going to have a finite time, a random but finite time, almost surely finite time, at which you're going to see the first success, at which you're going to see the second success, at which you're going to see the third success, and so on. So in fact, we have T1 is finite almost surely, T2 is finite almost surely, T3 is finite almost surely, etc., etc. And you have countably many of them. Since countable union of null sets is null, in probability theory, we can also say it as countable intersection of almost sure events is almost sure. So the intersection of all those, T1 is finite, and T2 is finite, and T3 is finite, and everything is finite, has probability 1. So it's not just that you're going to have T1 finite almost surely, T2 finite almost surely. You have a universal almost sure event under which T1, T2, T3 are all finite. And if you have finite success times, if you're able to see all the successes, right, this means you're going to see every value of Sn. Okay? You're going to see some n at which Sn is 5. You're going to see some other n at which Sn is 6, at which Sn is 7, another n, of course. So in other words, you're going to see the value of S hitting every possible level, because the number of successes so far was 0. Now it's 1. Now it's 2. Now it's 3. Now it's 4. This means, indeed, that the limit of Sn as n tends to infinity is infinity with probability 1. So this implies also that the limit of the success process is just plus infinity. In other words, this process explodes, the success process explodes almost surely. Well, although this success process explodes, we know that its expected value is NP, its variance is NPQ. So if you look at the number of successes per trial in the, or let me say, fraction of successes. Okay? Fraction of okay, let me say it the other way. Number of per trial. But it is a ratio in the first n trials. Okay? So it's a ratio which changes as you increase n. So what is the expected value of this? Just P. What is the variance of this? What is the variance of Sn over n? So what I'm trying to do is to motivate you for the next chapter, which is convergence. So if you let n go to infinity here, this variance just vanishes, right? Pq over n. Whereas this is a constant over time. So next chapter will tell us that Sn over n converges to P with probability 1. And this is called the law of large numbers. Okay? So P is deterministic. Sn over n is random. But this Sn over n converges to P with probability 1. In other words, you look at Sn of omega divided by n, and let n go to infinity. This sequence converges to a deterministic number that is just the probability of success. Okay? And in fact, this is a justification of the so-called frequentist approach for probability, namely that if you'd like to estimate the success probability of getting heads in each trial, what you can do is to calculate, run an experiment, okay? Count the number of successes by time 10, by time 11, by time 12, and calculate this ratio. So this ratio is going to converge to some number as you increase n. And the value that it looks like converging to is going to be the true probability of success. Okay? So that's why we can estimate the true probability by this ratio. Okay? And the estimation gets better and better as the number of trials increases. Okay? So this is going to be law of large numbers. Okay, but right now we're done with this chapter. Chapter 5 is done. Okay? So that was just a brief intro to stochastic processes, and that was the simplest type of stochastic process that you might have encountered in undergraduate courses as well. But already this very simple process shows a lot of nice behavior, such as this stationary independent increments property. So many processes are indeed Lévy. For instance, Poisson processes are Lévy. Brownian motion is Lévy. Okay? They also have stationary and independent increments. Okay? And just using a Poisson process or something that is Poisson and a Brownian motion, you can generate a lot more than those two processes that are still Lévy. Okay? So all Lévy processes can somehow be can somehow be constructed from a Poisson process and the Brownian motion. What is also nice about this process, Sn, is that if you take limits of this process properly by playing with the success probability and let n go to infinity, etc., you can get a convergence to Poisson process, and you can also get convergence to Brownian motion if you take two different types of limits. So in fact, this very simple, nice process can be used to construct. So if you have a family of such processes, you can use them to construct those Poisson and Wiener processes. So Wiener is the other name for Brownian motion. Okay? So there is, in fact, a nice idea behind working on this process. Although it is very simple, it is the building block of almost all stochastic processes. Okay? Let's say the canonical stochastic processes. Okay? Any questions about this chapter? Okay. So then comes convergence, our last chapter. So this is chapter 6, convergence. Of course, convergence of what? Convergence of random sequences, right? Namely discrete time stochastic processes. But before jumping into convergence in random sequences, I'd like to just give a brief recall on just the usual convergence of numbers, real numbers, okay? So the first one is almost sure convergence. But before even discussing this, we're going to look at just real numbers first. Convergence in R. Okay. So let's say we have a sequence of real numbers, although many of the results I'm going to recall are also valid for extended real numbers. So when I say a sequence in R, this means every member is in R. Okay? So recall that we have the relationship between inf sup, lim inf, lim sup, etc., etc. So minus infinity is less than inf. Which is the greatest lower bound, right? So this is less than lim inf. This is less than lim sup. And this is less than sup. And this is less than plus infinity with equality, possible equality. So although you have a real sequence, it can still have supremum equal to plus infinity. If it's an increasing sequence like 1, 2, 3, 4, and exploding, then the sup can be plus infinity. So also remember that lim inf was just sup of infs in the following way. So you look at the inf of the sequence after index n, and this way you get an increasing sequence. So its supremum is also equal to its limit. So this sequence is increasing, although this itself may not be increasing. And similarly, this is the inf of sups, which is also the lim of sups. Again, this is a decreasing sequence, so its limit is equal to its infimum. I think in one of the earlier chapters, we even showed that if you have a monotone increasing sequence, then its limit is equal to its supremum. And if you have a monotone decreasing sequence, then its limit is its infimum. Okay? So that's why this lim sup is inf sup and lim inf is sup inf. And we can just write lim sup and lim inf. Okay? So we say that, so we say xn has limit x, where x is some extended real number, if the lim inf equals the lim sup, and they're equal to x. And if we also have x being a real number, then we say xn converges to x. Converges to x. Right. So if the limit is plus infinity or minus infinity, we don't say convergence. We don't say that it converges to x. We just say the limit is x. Okay, so that is one way to talk about limits. But you also have this very old definition of limits using epsilons and deltas, or epsilons and n's. So let me also recall that. So we have that limit xn equals x, where x is a real number. Okay. So, okay. So, okay, let me first recall this one. So epsilon, for every epsilon, we have an n, and 0, let's say, such that after n0, we have the difference between xn and x is less than epsilon. So for all n after index n0. So the distance between xn and x is less than epsilon after index n0. And between index 1 and n0, maybe some of them are less than epsilon, some of them are greater than epsilon. But what this is saying is that we have xn minus x greater than epsilon for only finitely many indices, right? Because after this index, we have infinitely many indices. And before that index, we have only finitely many of them. So in only finitely many of them, we can have the reverse of this. So for every epsilon, we have xn minus x greater than epsilon for all, this is less than epsilon for all but finitely many n, or let me say it the other way around. So this is greater than epsilon only for finitely many n. Why do I say that? Well, because I'd like to have a nice way to write down convergence. So if I look at the indicator of this set, epsilon to infinity, so if I look at epsilon to infinity, okay? So those values, xn minus x in absolute value, is here for only finitely many n. And it is here for infinitely many n. Therefore, if I add those indicators from n1 to infinity, I should get what? I should get what? So these are going to give you 0 if the distance is less than epsilon. These are going to give you 1 if the distance is greater than epsilon. Finite number, exactly. So this is going to be a finite number. And the two statements are just equivalent, right? So let's keep it here. We're going to use it in almost sure convergence. So let's keep it as a useful way of rewriting this limit. And okay. One more thing. So, well, if you know it, so since real numbers with the absolute value being a metric is a complete metric space, being convergent is equivalent to being Cauchy. Meaning that xn is convergent, meaning that it has a real limit. Okay? It has a real limit, if and only if it is Cauchy. Is Cauchy, meaning that for every epsilon, there exists some index n0, such that after this index, we have the distance between xn and xm. So I take two indices after index n0. The distance should be less than epsilon. And this concept is the same in general metric spaces. You just replace absolute value with some metric. Okay? But for now, the real numbers with the absolute value is what we're looking for. Just recalls. Well, if you don't know what complete metric space is, just ignore this and see it as a fact that we just assume. Convergence is equivalent to being Cauchy, meaning that we have this property. Okay? Okay. And also for real numbers, I'd like to also give one result which you can use as a test for convergence. And that's going to be it about real numbers. Okay. Okay. So here's a proposition which I'm going to refer to as test for convergence. So let xn be a sequence in R. And suppose there is a sequence epsilon n. So I don't use a single epsilon. I use a sequence of epsilons of strictly positive numbers. with the following properties. So the sum of epsilons is finite as an infinite series. And we have that. So if I look at the indicator of epsilon n to infinity and check if the distance between xn plus 1 and xn is greater than epsilon n, and I do it for every n. So I use a different test value epsilon for different indices, okay? So it's different from what we did here, but it's a variation of that. So here we were using the same epsilon all over the time, so for all n. Now we change the epsilon. So this should be finite, okay? Then xn is convergent. For the proof, all we need to check is that this is Cauchy, because convergence means being Cauchy by this remark. So enough to show that xn is Cauchy. And for this, let's pick an epsilon. So let me first do this calculation that we need to do. So we'd like to show that something is Cauchy, right? Something is Cauchy. So we need to find an index. So find some index using those assumptions. So let me call it n0, okay? Such that for all k greater than m greater equal n0, we want the following. So we want this. What do we want? We want xk minus xm being less than epsilon, right? This is what we'd like to ensure after some index n0. So we're looking for such an index n0 for which this happens for all k and m. Okay? This is what we would like to show. So how can we do that? So I just assume m is somewhere here, k is somewhere here, and n0 is here. Okay? So let's try to go from m to k. M to k, how can we do that? Well, we can see it as xk minus 1 to xm plus 1 minus xm. And by triangle inequality, for absolute value, this is the sum of absolute values. Okay? So using the fact that this distance is going to be less than epsilon most of the time, so using this fact, let's call it number 1. So using number 1, I'd like to be able to bound these by their corresponding epsilons. What is the corresponding epsilon of this? Epsilon n. So this is epsilon k minus 1 to epsilon m. This is what we'd like to bound them by. Okay, so which index was the smaller one? M, right? So this is epsilon n from n equals m to k minus 1. Okay. And I can also bound this by n from m to infinity, let's say. So now I'd like to have this less than epsilon. Okay? And for this, we're going to use number 2. Number 2, where is number 2? It's here. Number 2. So let's use number 1 and 2, okay? So what does number 1 say? What does number 1 say? What does number 1 say? So this infinite sum is finite, meaning that this distance is less than epsilon for infinitely many n and greater than epsilon for only finitely many n. So this means there exists some, let's say n1 for this number 1, such that xn plus 1 minus xn is less equal epsilon n for all n greater than n1. So after some index, we're never going to have this is equal to 1. Okay, and let's use number 2. So since this is a finite sum, since this is an infinite sum, I can see it as the limit of its finite sums. So n1 to k converges to n1 to infinity, right? So this means there exists some n2 such that the difference between the limit and the finite sum, let's call it k, which is indeed from, so let's call it k minus 1, and then this is going to be k, right? So 1 to k minus 1, and then k to infinity. This is going to be less than epsilon for all k minus 1 greater than n2. Right? This is the term that converges to this limit. Therefore, the difference between them is less than epsilon for large k. Large k. And I just wrote k minus 1 instead of k here because I'd like to start this sum from k. Okay? Or let's call it even m. Let's call it even m because I just saw that this is m. Right? So in other words, m is greater than n2 plus 1. So if we pick our n0 as the maximum of n1 and n2 plus 1, so let me write it somewhere. Okay. So if pick n0 as the maximum of n1 and n2 plus 1, then we really have this inequalities with number 2 and number 1. So that we are done. We were to choose some index n0, after which we have all of those. And now if I choose my n0 as something larger than this, and also something larger than this, we always have those inequalities. Okay. So that's the proof of the test for convergence for just real numbers. Okay. Okay. Any questions? Okay, so let's give a break, and then we're going to continue with the actual convergence we're going to discuss.